Thank you, Jin-Ping, for taking time to do this with us. So I will first introduce Jin-Ping to the audience. For those who don't know her, Jin-Ping received her, I'm reading on her impressive resume here, like a CV here. She received her PhD degree in electrical engineering from Yale. And after that, she did a postdoc at NIST, which she then switched to the industry. She was in the academia, and then she switched into the industry in 2004, where she then has been a senior engineer and technical leader employed then by Infineon Technologies. I believe it's a German semiconductor company, and then IBM, respectively, with the IBM Alliance. Dr. Han has led the development of advanced technologies which had a critical impact on major products such as IBM servers, as well as mobile and automobile electronics components produced by IBM partners such as Samsung and ST Microelectronics. And since 2015, Dr. Han has dedicated herself to leading research projects that are fundamental to future AI technologies at IBM T.J. Watson Research Center, which ranges from algorithm exploration to hardware development. Dr. Han has co-authored and co-presented more than 140 papers at conference institute presentations in total, and which also included more than 58 peer-reviewed papers. She has also co-invented about more than 115 US and international patents. Dr. Han's achievements have been recognized by various awards, including Technology Rising Star Woman of Color, STEM Outstanding Achievement Award, the IBM Outstanding Technical Achievement Award, Infineon Inventor of the Year Award, and the National All Collegiate Inventor Award at US, sponsored by the B.F. Goodrich Corporation and the Inventors Hall of Fame. And then 7 months ago, she got promoted to Principal Research Scientist at IBM T.J. Watson Research Center. Jin-Ping, I'm going to hand the time over to you right now for your presentation.
Thank you so much for your nice introduction. And good morning, good evening, whoever is in whatever place globally, I guess. And today I'm so honored to just present a few charts which covers the bigger picture of what have been involved and what I'm currently working on and what may be the future. And it's kind of long journey of the semiconductor chip technology development to innovative design from mobile and server computing towards industry 4.0 and generative AI. And I'm currently, you see the smiley face. I'm currently in this building, in that floor, my office, and say hi to everybody. And what's the current in computing and what's next in computing? There are so many different versions of definition from our point of view. Computing, the current one, evolved in the conventional computers or supercomputers, which involved in so-called bits. And a lot of people who are familiar with, especially majored in math or information, are really into this bits things. And for IBM specifically, they have this Blue Jeans C series until Q series, and the mainframe P series until Z series, and currently still going on. And that's the bits. And next one is AI system, which is so-called the neurons. And people who have background with biology and information and may maybe very, very much enthusiastic in this area. And the IBM first on-chip accelerated AI processor is called the Xeon, was announced a couple of years ago. And the third one, and it's a big thing, but I won't touch too much on that, which is quantum system, and quite a large group of people working on the quantum IBM Q, which is more in a combination of physics plus information. So that's the current one. And the future one is what's the future one? It has to be all three combined together, and with some accelerated discovery in science, hybrid cloud, and AI-driven automations. So that's what's the big picture of this computing domain supposed to be in our definition. In terms of the AI system, because currently I'm mainly on the AI system domain, and AI system can be software, which is data plus code, as many of you know, and yet 1% of the AI research probably is on the data part, and 99% of the research are on the code parts, including the training a model or developing algorithm. Yet, AI system with only software may not solve everything, and there's the hardware part. And hardware currently is CPU, GPU, and memory, which is mainly on the DRAM side, and they have the data intensive transformation, communication across the whole the system over there, and it has its bottleneck. And for the future, that's why people are looking to all the different options. And one of the options we also got involved a bit. One of them, not all the options. We were thinking either it can be a ultimate goal, or the really ultimate goal is to minimize the data communication flow and speed up as much as possible with the minimum energy. And then there's some exercise for doing the so-called in-memory computer and, to combine the GPU part and the memory part to be together. There are so many options. I won't get into details. Well, for the AI system, there's two options. One is the bottom-up, and one is top-down, but I think both supposed to work, and that's all the things involved in, from the very bottom materials device up to all the way to algorithm application and the workloads related, and up and down. Well, if you have architecture and package aspect in innovation, you may get a high power efficiency. And if you have technology plus design optimization, you get boosted performance possible. And there's a lot, the day before yesterday, we have a big symposium called the AICS 2023. IBM VP gave a talk, and he said, okay, we want to think of path to put 1 trillion transistors. Transistor means very, very basic element of the whole computing to give you 1, 0 kind of things. And in that sense, we really have to do a lot of innovations to get there. And look at the chart, history chart, and there you can divide the arrow into 3 portions. One is the arrow of PC, and the second one is the arrow of internet, which including the mobile and the data center. And the current one we are in currently is the arrow of AI with the deep learning and the GPTs. So I don't need to get into all the detailed technical part. And there are some other companies also push out to the to the roadmap, which before nanometer 2 nanometer, 1.4 nanometer technology, probably before 2 nanometer, everything can be technology driven. And when they call it Moore's law, and when you come to the 2 nanometer and below, it may have to be, they call it multi-die arrows. And in the in cooperation with Armstrong arrow, that's called the CMOS. So that's the big picture of this whole thing. Okay, that's it. Thank you.
Thank you very much, Jin-Ping, for that presentation. Yeah, it's always very refreshing to see something like this being worked at, by smart people like yourself. Now, before we dive in, I've got a question. How do you end up with IBM? Has it always been like a dream aspiration to work at IBM?
Not really. I think at the beginning of the career searching, I was thinking of going to academia, and that's why I went for postdoc. But during the postdoc time, I like the place I have been, and but over there I started to collaborate with IBM colleagues, and they sent us the wafer we characterized for them, and published the very nice top tier conference papers. And that led me into a opportunity to see if there's opportunity for me in the industry, but not for the manufacturing, but still doing some research oriented. And it turned out, yes, there's IBM T.J. Watson, and also IBM and Alliance formed so-called IBM Semiconductor Development and Research and Development Center, alliance with more than 10 big companies around the world. So that's how I thought I want to give a try and to see something really for real, not just for publications.
So was that transition from academia into industry easy for you, or was it?
Yeah, I think for me, because I only went to postdoc time, so that's the time I made the final call. Okay, I should go to industry.
Right. Okay. Cool. So, but why specifically, when you started your career, you were already in the semiconductor industry, or what was your PhD, or what's your studies at university related to this field?
Yes,
I see.
It's not directly related, but indirectly related. But all the preparations that I have done with my PhD can empower me, or has empowered me to jump into the work, get started pretty quickly. Yeah.
Okay. So can you share with us about your career path then, as well as your research path, the journey in your semiconductor chip tech development?
Yes, I can share with you. It's a kind of long journey, but it seems like time flies very quickly. And some paths are not really determined by myself, and along the way, because IBM and Alliance have been working on this semiconductor research and development center, and working on traditional chip technology development from so-called very large, not very large in any standard, but we call it 65. I joined 65 nanometer technology. We think it's very large, very old right now compared to the 2 nanometer. And until I think 2028 nanometer or 20 nanometer, we have the alliance. Everything seems to be working pretty well, but the cost went up so drastically, and a lot of industry decided to dump their, become a fabless of a fablet. And from that point of view, you have no choice, and you can either go to the manufacturing and to those places who still do the semiconductor manufacturing or development in either Asia or some countries, like especially Global Foundry and other places. Or you have to think of regrowth your skills. So at that point, I also engaged with some clients in Asia, one in China, one is in Korea, to transfer the technology we developed from this R&D center and qualified in the R&D center and transfer over to the manufacturing in Asia. So that's my second part of the journey, and one of the tech transfer evolved in the on-site, means not remote support, but on-site, and working together with all the talent in the client's location, and co-develop those technologies and qualify them on the manufacturer side. And after that, and IBM just spin off the microelectronics, and I was asked to come to the IBM T.J. Watson Research Center, and I asked them, what can I do? He said, yeah, you may have two choices. One, you can look into quantum. Second one, you can look into analog, the AI. By then, they don't call it AI, they call it cognitive computing. And I just thought, okay, let me try the cognitive computing. And then I asked for guidance. I said, what can I do? And it said, no, you go to explore. I felt at that moment, it's kind of scary because I don't know how to swim. But then they asked me to swim through a pretty wide river, cross the river. And I may not survive, right? So, but somehow when you are put in that situation, I think the survival motivation really
kicks in.
Takes in, and then you just survive. So I survived by growing all my skills and from the reading books, but also doing some real project. And over the years, and I think I grew quite a bit, and even evolved in the software algorithm, bio-inspired algorithm-related work for the speech recognition, and also some other projects. But all in all, IBM, the organization I belong to, have to deal with the hardware. So when the AI hardware center was established a few years ago, and I put in and try to help out with higher level, not really device level, but in the design portion to enable the best possible options or solutions for some bottleneck areas of the data communication. So that's how I landed.
I see. So previously you were at the IBM parent company, and then so your work were more on the the hardware development side, and then after that, when you were put in the IBM Watson Center Research Center, that's when you transition more into the design part. Is that what you're saying?
Yeah, partially translated transformed into design. That's in the later stage, but also evolved in some algorithm skill development as well. So both. And in another part is mainly the R&D center, small R, big D development driven. So you have the project, and you have the product evolved projects. So you have to deliver something for real. But in the IBM T.J. Watson Center, they are more into the big R, small D domain. So that's why I was able to grow quite a bit.
So can you enlighten us for the audience, like in this context, when you say design, what do you mean? Obviously, we're not talking about creative design, but are we talking about research design?
Yes, and there in the design part, so there are quite a few levels of the design, and in the chart I have that flow chart from bottom up, or let me see, if you don't mind.
Yeah, you can pull it up. Yep.
Yeah. So when you see here, the design evolved a lot of things. So see, for example, if you see, the design can be a device design, and that's my early journey engagement. But then later on, you have the unit cell, like bigger than the device. The device is a basic cells, very like a brick for building a house. Well, the unit cell is kind of a framework in the small blocks. And then the array is you have an array of things and to extend furthermore. And then there are also some foundational, sorry.
No, it's okay.
Foundational IPs. And above that, there's also core and accelerator IPs. And above that, there's also the chiplet related. Chiplet means in the past, we have really system on chip, everything packed in one chip. But then later on, they figured when the technology started to scale down, and in order really to make the high yield chip, you may be better to cut into small pieces, so you have a high yield. Plus, you can pack some chips from older technologies, and some from very new technology, and some from mediocre technology, and you can put them together and get the performance you want. So a lot of innovation can be from there as well. And this chiplet alone is to include the we call it I/O, input output, kind of interface to communicate in order to enable the communication between those different block of chips, the different functions of chiplet to to communicate with each other more efficiently with the lowest power efficiency. So my main part is currently just the last month we delivered something in this domain.
Right. So in this regard, do you think that right now in the current market where there's a strong pursuit of AI by, everybody, in the academia, the research world, the marketplace by startups and, large corporations, how do you see the role of the innovative chip technology would play in order to meet that, AI advancement demand?
Yes, I think that's a very good point. And if you see the trend chart here, there's so many trillions of transistors to be put on. But in order to pack so many transistors, and you need to create a room for that. And if you just go to the traditional way, and there's basically your home is full of people. Your home can host probably 10 people or 20 people maximum. And but if you want to really put them in the room, like 100 people in the room, it's just impossible. So you need to think of how to put them into the one room. Either you can build second floor and go vertically, or you can dig a ground, right? So that's the innovation kick in. And also from the technology point of view, a lot of things, when things are getting so small, you may not be able to
compact
make
them
it
further.
work. Yes,
right.
If you make one device work, but you may not make 1 million device work.
Right.
Anyway, so a lot of challenges.
Right.
And you have to think of how to overcome that to make all the things work. And that evolved in all the innovations. Just like, for example, here you see the devices used to be vertical, and the so-called FinFET, probably you learn these terms. But then later on they think, oh, that's not, even this way is not enough. Previously it's just a plenary, and then they make it FinFET. And after FinFET, we realized, no, that's not enough. Now we have to get this kind of stacks, they call the nanosheets. And after here, this almost at the 2 nanometer range, and then they say, okay, now we use up all the space too. And then what else we can do? And then we may go vertical again in another dimension, like a so-called Z dimension. So those kind of things are innovation heavily involved as well. Yeah.
I'm glad if you could stay on this slide, because I'm actually quite glad that you're sharing this diagram, because I have a few questions that actually I want to talk about that pink arrow, because obviously we're now at that light blue big bubble here. We're like 2023, right? So obviously we want to move ahead. And, so I guess that's the $1 million question, right? I mean, like what kind of innovation can we go further? So this is where I want to get your thoughts about China's latest light-based chip invention that can perform at much faster speed and, also being more energy efficient. Can you sort of like talk to us about that? What's that? How is that technology different? To this.
For that, China's latest one, actually, honestly, I haven't followed up that closely yet. I may not comment too much from there. But in general, that come to the next pictures, which I mentioned here. And before 2 nanometer, and the technology by itself can really bring up to that domain. But once you come to this 2 nanometer or 1.4 nanometer domain, and you really have to think of system innovations, the design in terms of the system or in terms of the chiplet, in terms of all sorts of stuff. And in the system domain, you come into 3D, for example. And you come into place all the chiplet in the best way possible, that it can accommodate trillions of transistors, yet still give you the best performance you want for the era of AI. So that's the directions we have to go. That's why we put one chart from the MD here, and clearly you have all different triplets and also have to go 3Ds. And in going 3Ds, there will be a lot of challenges as well, especially the thermal, because when you put things on top of each other, when those processors are super fast, it generates a lot of heat. Yeah, those heat cannot be cannot be cooled easily in some sense, especially go 3D. So those also provide opportunities for people to think of innovative way to solve the problems for the heat issue, and they can move on as well.
So do I understand this correctly? If we're looking at the diagram on the bottom one, you're saying that if the transistor gets more than 2 nanometer, more than 2 nanometer, let's say it's more than like 14 to 10 and stuff, like you can no longer just think about just the chiplet, but also like a ecosystem play that's surrounding the environment, the system to support the chip. Is that right? Advancement of the chip.
Yeah, I think it's right. I can also add on a little bit regarding this chart, and this is only one company I use as examples, and there are some other companies who may not really believe in these options too. In addition, the bottom part is mainly from the transistor device levels and how the device innovation comes along. But when you see the chart and when you come to this range, and it seems like everything gets saturated, right? It's flat out. But yet you still want to pack so many things, and you have to really increase this interconnect the triplets and pack everything together. And that come to, you can call it the ecosystem in a small domain, but in other words, it's more like a system architecture, topology levels. Yes.
So do you then see in way forward, it becomes also more of a material issue, like a challenge, because you're trying to pack.
Materials certainly will play the roles, but the design by itself
too, of course.
Also, but the technology and the design of technology and the system have to be co-optimized in a way that it can work together.
Right.
That's why here has two terms. And one is called DTCO, another one called STCO. DTCO stands for Design Technology Co-Optimization, and STCO stands for System Technology Co-Optimization. All this co-optimization involves innovation.
Now, when I was preparing my question to ask you, I didn't know that you were preparing this, so I'm actually going to jump ahead, and ask one question since we were on this topic. So, in your view, in way forward, since we talk about obviously, material will become a challenge, especially when you have to pack all this, like into a small object. So when do you think the chip will ever be replaced by something else? That the material of the current chip will be replaced by something else that will be more lightweight or smaller and more sustainable, yet at the same time powerful.
That one I can really not predict, but I go back to the first page, and that's come to the picture of the
Of
quantum
this. Yep.
too, because that's also is taking place, and people are very hot on chasing after this one as well. So at some point, these three have to come together. That's
right.
Yeah. That's what we think of the future direction.
Right. Understand. And so obviously all this, what is powering and allowing all this large scale training models like deep learning to happen fast on this systems. Now, can you enlighten us a bit about IBM's hybrid cloud system solutions?
Yes, I think the hybrid cloud, I'm not an expert in the hybrid cloud by itself, but because our technology also serve the purpose of enabling a hybrid cloud in some aspect. And we know we have to really put the AI system into that hybrid cloud technology domain so that we can also enable the hybrid cloud from or enable it into the AI eras. And in addition, we also have to think of differentiate IBM hybrid cloud with the other competitors' hybrid cloud, and a lot of IBM own innovative system level and design level and the entire framework will be different.
Okay. Right. Can you unpack a step back to explain what a hybrid cloud is? Because for those who don't understand hybrid cloud, are we talking about part cloud and part something else?
As I said, I'm not the expert in this area, but my understanding is IBM's hybrid cloud is mainly for the enterprise, and the top priority of the hybrid cloud for IBM from IBM is security, and security.
I see.
So that's the very basic words, the keywords I learned from. Yeah.
I see. Wonderful. Before we take questions from the audience, which we already have collected a few. So I want to encourage the audience, if you're listening in from our Zoom room or from Facebook Live, please keep those questions flowing in. I would like to touch on intellectual property topic a bit, since you have filed more than 100 patents yourself throughout your career. Do you think that in this field that you're currently in, researchers should always be concerned about patents and IPs from day one? Because obviously, even some of the questions that I'm asking, I believe some of them are probably sensitive for you to even talk about, because of you have to protect some of this research knowledge work by IBM. So yeah, can you share with us about that?
I think the IP is very important for any companies,
mm,
if those IPs are high value IPs,
mm,
but in order to get high value IPs, the employees are encouraged to brainstorming and to come up with IPs, and then there will be a board to judge if your IP is good enough to go ahead for a patent, or it's just something you can publish, but not too much value for business. And for company, I think the IP is very important, but for university, I'm not quite sure if the IP is
right. So
critical.
interesting a remark. So how then do when the universities are collaborating with the companies, there's always this question about IPs that is raised by the university, because to them, they may think that it's very important. So how then do you think that these parties should think about this issue when you're trying to when let's say the researchers and the from both the universities and the companies are really passionate about an issue or a problem that they're trying to solve, but then on the management and the leadership level, especially let's say sometimes it can be more on the university front, that their main concern is about filing patents and IP, but that could be a hindrance to the whole research work. So how do you think, in your experience, we should think about that?
That's a good question. A simple answer is before collaborations, the university and company like IBM, they always have to sign a joint research agreement. And in the agreement, you have to define all the IP rights very clearly. And then after that, there won't be any dispute. So it depends on how the agreement is signed.
Okay, wonderful. But at times, do you think sometimes talking about IP in such early stage, even though it's important for business and companies, because in business, in a marketplace, and IPs and patents, they're sort of like a anti-competition sort of protection tool, right? But in the research domain, does this sometimes too much focus on IP at the early stage can actually create a hindrance in the research work, you think? Or it's just a matter of trying to align the interests here?
Personally, I prefer the IP is the product of the research. So your main focus should be the research or development and the project by itself for the business impactful outcome. But along the ways, you can come up with quite a few IPs, and that's very good. But some people indeed try to just come up, brainstorming and come up with all kind of IPs, and many of them, and some people probably can become a number 10 in the world, and thousands of patents in their lifetime. And that's another way, that's their choice. And if the company encourage it, still support it, then I'm good with it. But for myself, I only like to come up with the IP which I personally believe in, and which would have a big impact, relatively high value in terms of business impact. Yeah.
Right. Thank you for that, Jin-Ping. Right. So now I will take question, and I'll start by looking at the first question that were asked by the audience. The first question here for you, Jinping, is how are semiconductor manufacturers addressing the challenges of power consumption, heat generation, and reliability as chip complexity and performance continue to increase or advance?
It's a very good question, but also it's very complicated one because there's all sorts of uh, innovations. And if you just look into the patent, as you said, there's tons of patents addressing those issues. So they want to protect, even they don't realize the technology, but they think those are good ideas, which they got pilot data to support those ideas. They just patent them already. So I think along the development of semiconductor device and technologies until the design innovations, and we have really worked out quite some solutions to qualify those technologies. And one of the biggest one would be or have been and has been reliability. So there's a very comprehensive set of the tricks or secrets to address those issues. And if the reliability is not demonstrated, then your technology cannot be put in product.
Right.
That's
of course. Thank you for answering that. Now, the next question is, what role do advanced packaging technologies play in enabling the integration of multiple chips and functionalities into a single package? Very technical questions on this.
Very good one.
Yeah.
And that's what people in this area try to figure out as well. And there are so many different ways. And for the advanced packaging, and people have developed things called I don't know if people are familiar with the silicon interposer. And in the silicon interposer, there's also all sort of through silicon via, we call the TSV. And those TSVs has a certain range of how close to those each TSVs are to each other, and those called the pitch. And this pitch itself can shrink to an extremely small, or can be relatively large. You can imagine when you have a very small ones, and the entire density will be much higher. But then it also has some challenges like signal integrities and their interference of the close by vias and all those communication channels, and there's some signal loss and all sorts of things, and we have to address as well.
Right.
So in addition to that, there's also quite something regarding to the bump. You have different layers, and you packed on top of each other. Probably some people knows this. In between, there's some bumps, and currently that's the standard ones. You pack them together. But when you come to the advanced technology, one example is you don't have the bump anymore, and you just have some copper put on top of each other. They call it hybrid bonding or direct bond, and some of them just called the bumpless way. Those it's another version of innovation from the advanced packaging as well. So I cannot go along the way. If I have 5 hours, I can go.
Of course, but I think that's a good enough answer for us. And The next question here is how can semiconductor manufacturers like IBM collaborate with software developers and system integrators to ensure that the hardware and software are optimized for specific applications?
Yeah, that's a very good question, and I probably touched upon previously. And in the chart, that flow chart, and all the areas I mentioned involved in the collaborations. And IBM is not really a hardware company, and they have expertise from all the areas, so we can easily collaborate with. We can easily collaborate with the IBMers in the different areas. Meanwhile, we can also collaborate with the universities or the other companies and to co-optimize the entire system, especially the vendor, because IBM has all the experts, but they don't generate their own tools. We have our own tools for our own purpose, but we want to still open to the outside world. So we have to use some open source tool set. So in that way, we have to collaborate. With that.
So if there are companies who wish to do that, how, in your view, where should they start? How should they, engage IBM? Do they start by IBM Watson Research Center to say, hey, can we work with you? Can we send a proposal to look into this issue together?
This business part, I really don't know too much. But I do see, for example, today, right before I come here, that's why I was kind of in a packed schedule. And today we have the entire AI hardware forum annual event, and a lot of companies, clients, potential clients, or the existing ones, come together and learn what's the newest technology or the systems or AI related whatever potential products are all there, and what may be the challenge spots people can champion, and they come to learn and to engage with the people here, and then they may find some chemistry among the during the engagement, and that probably can trigger some collaborations, and for the better business for both.
Okay, so for that person who asked that question, I hope that's Jin-Ping's answer, a satisfied question. And obviously, if there's anybody who's listening and you wish to explore collaboration with IBM, I suppose you just have to look at their site, do your homework, and I think you can always reach out. No harm done there. And as what Jin-Ping has said, they are looking into collaboration, so you just have to find the right channel, talk to the right people.
Exactly.
Right. The next question. Okay. Recently, Apple replaced their computer CPU chip from x86 CPU architecture by Intel to their in-house design of ARM CPU architecture because of its efficiency. So even companies such as Google, Microsoft, Amazon, Oracle, etc., are now providing web servers with ARM CPU architecture. Do you think ARM CPU architecture will completely replace x86 CPU architecture?
I'm not quite sure if that's the the expertise area I can answer, but from what I have observed, there will be ecosystems allowed for more than one companies or one architecture to dominate the whole world, including people talk about the RISC-V and other potential developed architecture to begin with. Although the architecture always come along with libraries. The libraries are contributed by different ones. Personally, I also see a future out there for the open source ones. Keep an eye on that. It's not a bad idea.
Okay. So there's another related question. Nowadays, GAN chargers, like GAN, has emerged where the chip is made of gallium instead of silicon, but computer chips are still using silicon. Will gallium replace silicon in computer chips? If so, how soon do you think it will be replaced?
I think it's for different applications. I wouldn't think it will be replaced in the mainstream, but for niche applications, certainly yes.
Okay.
And especially, for example, currently they are working on the power applications, and it's already there.
Are the devices that we have at this point in time ready to support the AI tech at scale?
I'm not quite sure if I get the question correctly. So, are the devices?
Yeah, are the devices that we have at this point of time ready to support the AI tech? So I suppose this person is asking, like, at the current marketplace, like current R&D and the technological advancement, do we have all the hardware to support AI tech? And I suppose here, if I could sort of like maybe help this to rephrase this question, let's say if we're talking about like a full-fledged AI application in let's say like we all have this industry 4.0 in mind, right? Let's say like we have a fully autonomous public transportation system, and then wherever you're going you have got high speed like internet connection, and then and then you could at any one point just pull up whether it's your smartphone, your computer, and you could start working while you're being transported from this place to another place. Traffic lights, everything just being powered by and by not just interconnectivity, fast speed interconnectivity, but there's also AI powering everything, so it just make the whole experience more better. So do you think at this moment our hardware devices and everything ready to support this kind of tech, IoT/AI at scale?
I think so. Although I have a little conservation regarding the power consumptions, because they used way too much of the power. And like people said, if you really want to do a certain AI, really the GPT, whatever 4.0 for some task, you really have to build an entire nuclear plant to do that. So this is my biggest concern. Yes, that's one of the innovations we are moving towards as well to solve that power.
I'm glad you brought that up because Jin-Ping, I think there's a lot of times the general public don't understand like what goes the kind of computing resources that goes behind, let's say, like training the large language model that OpenAI is doing to produce, to release, deploy all this GPT, 3, 4, 5, this kind of technologies to the public. Actually, just to release one new ones, whether it's GPT-5, sometimes you could need, an entire power plant, just to power that. And yeah, so while we're thinking about, like fast, like intelligent, fast AI, I mean, should we at this aspect also consider about how more algorithms or models are being designed so that it can be more energy efficient, and then also at the same time that the hardware is also able to support it? Because otherwise, if you may be very advanced, let's say right now, like what OpenAI is doing with their GPT's technology, if they want to keep going further and further, so does that mean like you have to build warehouses of data centers and like not only 1 or 2 nuclear power plants just to support this technology advancement? So when do you stop? When is this becoming like something sustainable?
Yeah, it's true. So that's one of the concerns I have as well.
Mm-hmm. Mm-hmm.
That's why we have to really work hard to come up with innovative solutions to save powers when we come up with the AI, efficient AI hardware chips, systems.
Now we've got a few more questions here. One of which is will the innovation and invention of this new technology change this and shape how our devices and the way we use it as users?
I think I think the answer may be yes, but how we will use it and hopefully use for good.
For good, exactly, right.
Yeah, I still think the Earth, we need to pay more attention to be more friendly to the Earth. That will be my deep heart use case, which should be the first priority, rather than weaponized here or there. And also.
Yes. Exactly. I totally agree with you. And that's why I think the next question, it's very relevant. What are the ethical and societal implications of advancement in the semiconductor chip technology?
Yeah, I think a semiconductor chip technology by itself should be pretty innocent.
Yep.
But how do you use it after you come up with some product is the questions, and that come to the regulations.
Yep.
I would think the regulations has to be in place.
And sometimes have to be caught up with all this technological advancement to safeguard.
Exactly.
All this.
And the recent story about OpenAI CEOs in and out stories involved in all sorts of different things. Although I think probably 80-90% of the people are behind the new CEOs or the CEO. But there is something which are scary though. If indeed there's so-called a Q star come to be at the path of being out of control, then we have to see how to control this beast.
Of course. Now, Jin-Ping, we unfortunately, and we've run out of time, and I know that it's late on your end, and also I've learned so much personally about this industry, about your career, about what you do. Before we go, can I ask 2 last questions? One of which is when I was preparing for this session, I can't help but to imagine, like that chart earlier that you showed, that pink arrow. When do you think that we will ever reach to a point where, the design of the chip and the material that will be used will no longer be what it is today, like, based, done with silicon, or, that still plays and pack on, like, like some plastic chip. Maybe it can be done, on something as thin as a film, for instance, and then it could be, so lightweight, and yet still, like you've got enough, it still can be powered by, the electricity, so that it can, run on some very small and thin technology. When do you think such advancement could possibly happen? Are we looking at another 10, 20, 30, 50, 100 years from now?
I think that's possible in next decades also,
Mm,
because people are looking into the 2D materials,
mm,
2D transistors
mm,
at this moment already.
mm,
And I used to be very pessimistic about scaling,
mm,
and giving what all the innovations coming
mm,
along after our 20 nanometer or even 10 nanometers, we thought that's it.
mm,
But then it keep coming through, and due to all the innovations,
mm,
not only technology innovation, but also design innovations.
mm.
So I'm still hopeful, and it shouldn't be too long, into 50 years, but I
Mm.
think should be possible.
Right.
Until some point, they think uh, it's just a dead wall, it's a dead end.
Mm,
And then there's some other innovations from system point of view, from
mm,
from other aspect we kick in, and I think humans
right. No,
brain is really
amazing. Yeah.
amazing, really
Yeah.
amazing.
So one last question, which is, because I'm sure there are students and also aspiring researcher or scientists who may want to be like you. They have studied electrical engineering. And what are some of your personal advice that you would like to give all these young minds, future leaders of the tomorrow, if they want to build a career like yourself? How would you advise them to guide them, to build such an amazing career that you have? Mm,
Um, my personal experience may not be the best examples, but I would think if you want to learn uh, from me, and somehow I really think uh, the hard work
mm,
is absolutely necessary
mm,
uh, to enable you moving forward. And once you run into problems
mm,
or difficulties and challenges, obstacles, don't give up.
mm,
I personally never give up. Even sometimes I get it wrong, but eventually, and you believe if you can moving forward uh, with your persistency and with the skills you can grow along the ways, and
mm,
with the teamwork you have with around around you, or even through the family members or the internet friends,
mm,
and you should be able to uh, accomplish some goals which is important for you. And another
mm.
thing I think is you have to be passionate about what you are doing.
Right.
And even some work sounds so cool, but
Mm,
feels so boring
right.
in reality.
Right.
And
Of course.
you have to come up with some motivation and to move forward. and don't just rely too much on shortcuts.
Yep.
And something you have to work on it. So that's my basic experience. I know that's not really the best examples. Many young
No, Jin-Ping. That it's so well, grounded, and it's a very practical advice, and I think a lot of wisdom there as well. So thank you for sharing that. Yeah, thank you for making time for us. I know it's extremely late now, and you just shared that you had meetings back to back today. So I don't want to hold you further. So thank you, Jin-Ping, for your time and sharing your career journey with us, and also your experience and knowledge and your insights of the industry and the technology and the research as well. So thank you again for making time, and take care, and we'll speak soon.
Okay, thank you so much for having me here, and thank you everybody who spent time with me, and hopefully my answers are not so disappointing.
No, not at all. I'm sure. Thank you. Bye-bye.
Thank you. Bye.